Alright, this first algorithm we're going to cover is the k-means way of determining where the key is that's going to be replaced for the chroma key. So this is done first. We just load some images and get a key from the user. That's going to be the color that we are going to replace. We then convert the picture into the LAB color space, we extract the AB data, and then cluster the data together based with k-means. We do 3 iterations of that. We then combine any of the clusters together that have very similar values for the cluster center. So if they're both blue set to data, then it combines it together. We then find the clusters that are very close to the key, and if they are the one closest to the key, then that's the cluster that's going to be replaced. We then go through and replace all the values that have that cluster value and leave the rest of them the same. So you'll just see the picture where the cluster is not the same as the key, and then the background where the cluster is the same as the key. And that's essentially how this algorithm works. I'll go ahead and run it. The picture is going to be of a guy in front of a blue screen. You'll see a little bit of the background edge near it. And I'm going to pick the closest color to the background. Now it's running through the k-means algorithm to group all the pixels together. And it's doing this 3 times, 3 iterations to get the cluster means to the right place. So here's the results. This time it actually ended up clustering it into only 2 sets of data, so the clusters were close enough that they got combined. As we can see, all the guy in the backdrop are in one cluster of data, and then all the blue data is in the other set. The cluster 2 and 3 empty because they must have been combined with cluster 4 to make up the entire blue set. And here you can see the background blue replaced with the background image, but you can still see on the border there is some blue, and especially around the guy where he's smearing his hand with motion too, you can still see a little bit of blue that has not been replaced. Alright, in this second algorithm we are doing the chroma key with a axis rotation in RGB. So we open the image, get a user key, and then first thing we do is we take that key and we convert it into polar coordinates. So we create a rotation matrix based on the polar coordinates of the key. Then we do a rotation on the RGB space so that the new picture or the new axis that it's on is rotated so the key is on the x-axis. We then convert that entire new axis into polar coordinates, and then we compare the angles to the x-axis and see which angles are close enough to the x-axis to be considered the key. We then take all those values and then find the median value and assume that is actually like the true color of our background, and we actually just rerun the entire process that we just talked about with the new key, and then replace the background. One thing we do extra here is that we actually multiply the background by the magnitude of the luminosity of that axis, so we actually get some of the shading from the original thing. So we're going to run this same image that we used before, but this time we're going to replace it with a red background. So first time through the algorithm you can see that it didn't get all the blue background, but it got close enough, and so it took the median of all these white spots and then redid the algorithm and got a better result because of that. So here you can see the red background, which is supposed to be solid red, but we actually have some shadowing and stuff on it. That's due from the shadowing that was on the blue before. All these lighting effects actually got transferred over to the background. The third algorithm we're going to cover is just the color segmentation using the k-means and the lab color space. This actually follows just like the first algorithm. We just open up, instead of the background, we open up one set of textures that we're going to replace the clusters with. Same idea, we open up the picture, convert it into LAB space, and then do k-means clustering on it. The only difference is that at the end, we just replace each of the values that they're clustered to with one of the textures. So I'm going to run this real quick. I use a little bit smaller sized picture than I did for the results in the PowerPoint. But kind of here's the idea, is that it takes and clusters the data based on the colors, and as you can see, as discussed in the results, it's hard to tell between the dark and light colors, and then it just replaces it with the texture. The fourth algorithm and the last algorithm we're going to cover is the grayscale thresholding that's used to segment the color. So we load in the file, convert to grayscale, and we do a histogram equalization on it to make sure that we got enough differentiation between different types of gray. We go ahead and load up a different texture. This time I have it loaded to the camouflage texture. We then threshold based on different gray values, and then we just do some replacement of the image with the new images, and that's it. So here's the results. The first image is the original image just turned to grayscale. Then we did the histogram equalization, not a huge difference in this case. It was already pretty spread out. And then we do our thresholding. In this case, you can see there is a big difference between the blackberries and the white on the from the light. So this was a better application for finding the blackberries. In this case, we just replaced with different colors to camouflage. So I want to thank you for watching this presentation. Once again, I'm David Barnette, and if you need to ask any questions, please just feel free to email me. Thank you very much once again.